we'll review. I think we talked about this a little bit in Organic 1, but we're going to go into it a little bit more depth in this course. But the same standard applies, is that my expectation of you is that you should be able to have recognition knowledge when it comes to naming organic compounds. Can you match a structure with the correct name? Or given the name, can you pick out the correct structure? That's what I want from you. Okay, so remember that carboxylic acids are abbreviated in a couple different ways. That's why I put it in your notes like this. You'll either see it as CO2H, or I tend to write it COOH. It's just a matter of preference. Okay, be aware of that. And the naming is based on the parent name of the alkane. So for example, if it's a 4-carbon chain with a carboxylic acid group on it, that would be butanoic acid, where you replace the E at the end of the alkane name with oic acid. And just like aldehydes, you do that, and you also define what carbon number 1 is. So the carboxyl carbon atom becomes carbon number 1. So here's just some examples, so they get complicated. You see this one over here on the right with the 2 carboxylic acid groups. You would actually have a longer chain, oh pardon me, you would have the same length of chain if you incorporated the ethyl group into the longest continuous chain, but that means that you would be leaving out the other carboxylic acid. So it does get complicated. So once again, my expectation is recognition knowledge, multiple choice, matching kind of a question. Okay? All right. So what if you have a ring? Well, then the naming is different. You name it like the ring, but then you just add a suffix, carboxylic acid, to the name. So compounds with the carboxylic acid bonded to a ring are named using the suffix carboxylic acid. Okay, and in this situation, it's not numbered because it is a substituent. It's considered a substituent if it's on a ring. And another term that is often used to refer to carboxylic acids when they are a substituent is just the carboxyl group. So as a substituent, the CO2H group is called a carboxyl group. And if that's not complicated enough, now we make it really chaotic because there are lots of carboxylic acids that go by the common name. For example, acetic acid, we talked about acetic acid. And then lactic acid, again, has applications in biology and physiology. So, don't get too comfortable with the naming rules because many times, those just get thrown out and they use the common name. So a situation where you would have the carboxylic acid as a substituent on a ring is this, the 1-cyclopentene. We name the ring, and then we just throw the suffix on their carboxylic acid because it is a group that is a substituent on a ring. And then again, just if you want to know what lactic acid is, nothing to do with the structure. It's because they knew about this acid long before they knew about chemical structure. All right. Okay, some other just properties of carboxylic acids that turn out to be important for their chemistry. We'll go back to this idea of the geometry, which is based on the hybridization. So carboxylic acids are sp2 hybridized carbons, or involve an sp2 hybridized carbon, which means it's trigonal planar and therefore has an ideal bond angle of 120 degrees. Okay, another important property is the fact that they can both donate and accept hydrogen bonds. That has that OH bond in it that can donate the hydrogen bond, and it's got 2 oxygen atoms in the functional group they have lone pairs that can accept hydrogen bonds. And so the consequence of that is that carboxylic acids typically have, relatively speaking, high melting points, boiling points, and solubility. Okay? And as the name kind of gives away, we know this, we've learned this before, that carboxylic acids are weak acids. They have pKa's in the range of 4 to 5. You can tweak them a little bit to get them out of that range, but typically a carboxylic acid will have a pKa in that range of 4 to 5. They're weak acids. Okay, and another highly exploitable property, as you'll see in just a minute, is that if you can remove that hydrogen from the functional group, that acidic hydrogen, then it becomes a carboxylate, which is another way of referring to that would be the conjugate base of the carboxylic acid. Remember that when an acid like carboxylic acid gives up its hydrogen that is the conjugate base. Okay, and that is going to be water soluble because you've got an ionic compound at that point. It's negatively charged. There'll be a positively charged counter ion, usually something like sodium or potassium. But what it does is it makes the compound much more water soluble. The conjugate base is typically water soluble. Okay, so for example, we've got a question like this. We have benzoic acid and you use it as the starting material to make methyl benzoate. Why would you be doing that? Well, because this is used a lot in perfumers, one of the components of perfumes and anything you want to make smell good. What technique could be used to purify it? Because otherwise, let's say that you're putting it in a lotion or something like that. You don't want to put benzoic acid on your skin. That would irritate your skin, right? You got to get rid of the benzoic acid. So how could you purify that methyl benzoate, which smells nice, from the benzoic acid, which doesn't have a smell and is going to irritate your skin? Well, you would exploit the property that we just talked about. How if I could remove that acidic hydrogen, then it becomes water soluble. So it will move into that, that conjugate base would move into the water layer. And then I could just purify the desired product that way, okay? So you would extract the benzoic acid with a basic aqueous solution and then use a separatory funnel. And we have done this in Organic 1, I know we did it, where, I can't remember what compound it was, but to get it to move into the aqueous layer, we just added an aqueous solution of a base, like sodium bicarbonate or sodium hydroxide would work. Anything to rip off that hydrogen, making the carboxylate, which is much more soluble in water, so it moves preferentially into the water layer, and therefore you could purify your organic material. This would stay in the organic layer. Like if you were using an organic solvent like ethanol, well, not ethanol, because ethanol would mix with water. Something like ethyl acetate, maybe. It would stay in that organic solvent layer, whereas the impurities, the leftover benzoic acid, would move into the aqueous layer. Okay, so extract the benzoic acid with a basic aqueous solution with a separatory funnel. And I just give you a little picture of that on the next slide. I don't think this is in your handout. No, it's not in your handout. But again, so you're making that, in this case, it's ethyl benzoate instead of methyl benzoate, but it's the same principle, but just pointing that out. So you're making this ester right here, but just, reality dictates that you're going to have some unreacted benzoic acid, but you need to get rid of it. So if you just add some saturated aqueous sodium bicarbonate, basically baking soda dissolves in water, you're going to get two layers because this organic layer is going to form, it's not going to be, soluble or miscible with the aqueous layer. So it will have its own layer where the desired product will be, but then any leftover benzoic acid, because of the reactivity with the sodium bicarbonate, that's a weak base. It's going to move into the aqueous layer, and then you just turn the valve to, get rid of that aqueous layer and harvest the organic layer, and you've purified your desired compound. Okay? Okay, so now we mentioned the carboxylic acids are acidic. So now let's talk about some things that could affect the acidity, how strong of an acid or how weak of an acid it's going to be. And it turns out that one factor is if the conjugate base, the carboxylate, is more stable, then it enhances its acidity. It increases its acidity. So factors that stabilize the carboxylate anion, also known as the conjugate base, result in increased acidity. Okay, so what would do that? What would cause that? Two things. First of all, an inductive effect. So if it's electron withdrawing, that's going to stabilize the negative charge because that electron withdrawing group is going to pull that negative charge kind of away from that carboxylate and towards itself. And so that's going to make it more acidic. And just the opposite with an electron donating group. Electron donating group is going to kind of push electron density into that carboxylate, which already has a negative charge on it. So that's not real good. So that would make it less acidic. That would make it less likely, less favorable for ditching that H plus and taking on the negative charge. But also recognize in this bullet, the other blank here that you need to fill in is that this is also dependent upon the distance from the carboxylate. The closer it is to the carboxylate, the more effect it's going to have. The further away from the carboxylate, the less effect that it's going to have. Okay, so things I already said, but let's just put them in our notes now. So electron withdrawing substituents, things like halogens, anything that can pull electron density towards itself, that's going to make it more acidic, which remember is a lower pKa. And then, as I said, Just the opposite with the electron donating substituents. Those would be things like alkyl groups, methyl, ethyl, T-butyl, anything with lots of carbon and hydrogen in it, that's like electron donating. So that's going to increase the pKa. And so here's just a couple graphs to illustrate what I'm talking about. This one is the inductive effect. So if you start with just acetic acid, its pKa is 4.76. But then if I start substituting these hydrogens with halogens, it lowers the pKa. If I do it with iodine, it lowers it to 315. But if you'll notice this, as I go down, or as I increase in electronegativity on the halogen, okay, because we're going up the periodic table, so that's an increase in electronegativity. So I get to the most electronegative element on the periodic table, fluorine, and it really lowers the pKa down to 2.66. So, throwing a fluorine in there stabilizes that carboxylate, makes it easier to rip off this acidic hydrogen, so the pKa is going to be lower. All right, but the bottom scale here just shows you how that inductive effect wanes as it gets further away. So the effect is less if the bromine, if the electronegative atom is, in this case, 3 carbons away. It's a little bit more of an effect if it's only 2 carbons away. 1 carbon away, it's 2.86 as we saw above. So there's an inductive effect, but it does wane as you get further and further away from the carboxylate group. Okay, now if you're talking about a benzene ring where you have a benzoic acid, then it's very similar to what we talked about with the activating versus the deactivating groups. If something is a deactivating group, okay, it's actually going to make the hydrogen more acidic because those are electron withdrawing groups. The reason why they're deactivating is because they're electron withdrawing. And so that's going to ultimately pull density out of this OH bond, making it easier to rip that hydrogen off of there, and that results in a lower pKa. Makes the hydrogen more acidic. But it's just the opposite when you've got an activating group, again, and what made it activating is it donates electron density to the benzene ring. So that's good if you're trying to get a reaction, a substitution reaction on the benzene ring, but it does also make that hydrogen on the carboxylic acid in this instance less acidic. So it kind of depends just what properties you're looking for, One way to do it is you start with a benzyl group. So remember what that is. That's a carbon, it's like toluene. It's a carbon that's attached to a benzene ring. Those hydrogens, the reason why they're color-coded green, they're highlighted in green, is because those are easier to remove because of the stability of that benzylic position. And so therefore it's easier to oxidize that position. And so that's going to result in a carboxylic acid from just an alkyl group. I just start with an alkyl group and with a strong oxidizing agent, and there's several things that can do it. The dichromate, the Cr2O7 2-, or permanganate, MnO4-. It's catalyzed by sulfuric acid, and heat is usually added. I think that does depend on what the other conditions are, what other reactants you're using, but generally this kind of reaction you'll do hot, and so you get a carboxylic acid out of it. So you can oxidize an alkyl group into a carboxylic acid if you use a strong enough oxidizing agent, acid catalyzed with heat. Okay. Now the thing is, you have to have hydrogens there. So that's what the next picture shows. That if you start with a compound like this, where you've got this benzene ring with this is a T-butyl substituent. So let me actually make note of that. So this right here, is T-butyl, tertiary butyl. Okay. So there's the unique thing about this is that there's no hydrogens on that carbon. Notice that that carbon does not have any hydrogens on it. And so it does not get oxidized into a carboxylic acid. It stays the same. But this other alkyl group, because of that benzylic hydrogen, that's key. You have to have that in order to cause this oxidation. And so you do get the carboxylic acid as a product. So primary and secondary alkyl groups can be oxidized with these conditions, but a tertiary will not. So just be aware of that. And again, we've talked about these before, where you can start with an alcohol. If it's a primary alcohol, you can oxidize it all the way to a carboxylic acid with a strong oxidizing agent, okay, like this. Or if it's an aldehyde, you can oxidize that into a carboxylic acid. Okay, so oxidation of a primary alcohol or an aldehyde yields a carboxylic acid. Okay, so another way, again, we've gone over this before when we talked about granular reagents, but this is actually a pretty common way to make a carboxylic acid. You make the granular reagent first, and then you just, whatever solution has that granular reagent in it, you pour it over a chunk of dry ice. I've even done this, it's been decades ago, but I remember doing this experiment where you make a granular reagent and then you literally just have a beaker or probably an Erlenmeyer flask actually, and you pour the solution on top of a piece of dry ice and bada bing, bada boom, you get the carboxylic acid. So here's how it works. Okay, so the granular reagents react with dry CO2, dry ice to yield a metal carboxylate, and then you do have to follow that up with a work up step where you protonate that carboxylic acid, usually with a strong acid, or it just depends. So protonation by addition of aqueous strong acid in a separate step gives the free carboxylic acid. So something like this, where you have the granular reagent, in this case, it's the phenyl group or the benzene ring, and the carbanion attacks the carbon in CO2, creating the carboxylate. And then in the second step, you just displace the magnesium there. So what we need to do is we need to produce, this is the carboxylic acid functional group right there, remember CO2H. Okay, and we're starting with T-butyl chloride. So we've got a carbon that's got 3 methyl groups on it, okay, and a chlorine, okay, T-butyl chloride. And so then if we just react that with magnesium, and usually it's done in some ether solvent, and then the magnesium just inserts itself between the carbon and the chlorine. So again, we got the CH3 carbon, and then the other 2 methyl groups up top and down below. But now MgCl, so and now this is my grignard. Okay, and so then I just subject that in 2 steps. The first step, I'm just going to, again, just pour it over some dry ice, and then the second step, I'll just protonate it with some source of hydronium ion, some strong acid or something like that, and you end up with the desired product. So you got the carbon with 3 methyl groups. This is the T-butyl group. And now it's just got the carboxylic acid functional group. All right, another way to make carboxylic acids is that you cause the hydrolysis, remember that just means adding water, to a nitrile. Okay, and the way to do it precisely is that you have to heat the nitrile in an aqueous acid or base. So nitriles on heating with acid or base yields carboxylic acids. And a good example of this is what's in your notes there, the production of ibuprofen. So the first thing that happens to produce ibuprofen is you start with this, similar to what we just showed, this organohalide, okay, and you get an SN2 reaction. The cyano group substitutes for the chlorine. Okay, so the chlorine is your leaving group. You add the cyano group, okay, and then if you just heat that up with some water and in a base, the mechanism is more complicated than an acid, so I think it's usually chosen to be done in a basic solution, and it just transforms into a carboxylic acid.